Swayam Prabha. Digital India. Educated India.
Hello everybody. Today I am delivering you the third lecture of module 9. In the module 9 I was discussing about the surface of revolution, and in that respect I have found the differential equations of equilibrium, and then I reduced it to a axi-symmetric problem by with a special condition that n phi theta equal to 0 for axi-symmetrical loading on the surface of revolution. And on the basis of that, I have shown you how the analysis of a spherical dome, which is very common in application, can be done with the help of membrane theory using axi-symmetrical condition. So, today I will give you some further examples of surface of revolution under the action of axi-symmetrical loading. Okay. So, only I will consider axi-symmetrical loading case, so that you can the most of the cases in practical field are of axi-symmetrical nature, except the wind loading in our civil engineering structure, that is the dome. That wind loading becomes a asymmetrical case, that is it is not symmetrical with the axis of rotation. So, in that case formulation will be of different type, but so far we are discussing only the axi-symmetrical loading, and in that situation the formulation that we have derived or demonstrated in case of spherical dome will be applicable. Okay. Now, we know that under axi-symmetrical condition n phi theta equal to n theta phi is 0. So, that means deformation and loading of the shell is independent of theta, and in that case the three equations of equilibrium that we have obtained, one along the tangent to the meridian, that is the resolving the forces along the tangent to the meridian and equating them to 0. Again, resolving the forces along the tangent to the parallel circle and taking sum of the forces and equating to 0, we get second equations of equilibrium, and third equation was obtained by considering the sum of the component of forces to be 0 along the normal to the tangent plane at the meridian. So, these three equations we have obtained for any general kind of loading, but when we consider the axi-symmetrical condition that n theta phi equal to n phi theta equal to 0, therefore, all the stress and deformation external loading are independent of theta. So, therefore, equations have been reduced to number 2. And we have seen these are the two equations d d phi, the derivative of r n phi with respect to phi, minus r 1 n theta cos phi plus r 1 w phi equal to 0. So, it indicates that it is the equations of equilibrium obtained by summing up all the forces along the tangent to the meridian, because the component of the external load along the tangent to the meridian is w phi. So, that equation you can see it consists of only consists of two variables, one is n phi and another is n theta. But the third equation that I have told, the equations of equilibrium obtained along the normal direction. Normal direction, I mean here that the direction along the normal to the tangent at meridian. So, this equation fortunately was an algebraic equation, no derivative expressions or derivative quantities are involved in the third equation, that is the equilibrium equation along the radial direction. So, therefore, it is a simple equation n phi by r 1 plus n theta by r 2 equal to W r. Now, if you recall that r 1 r 2 are the principal radii of curvature of the shell surface, whereas r is the radius of the parallel of latitude. So, however, r is related to r 2 by trigonometrical relation that we have seen earlier also, and here also we will use it. W r is the component of the load along the normal direction that we call in the radial direction. Okay. Now, this equation after integration, before integration we want one more step. That step is that n theta is now substituted from this equation in terms of n phi, because this is a plane equation 1 by r 1 into n phi plus 1 by r 2 into n theta equal to W r. This is a plain algebraic equation. So, therefore, n theta can be expressed in terms of n phi, and we can substitute back here in the first equation. So, ultimately the first equation can be converted into a equation of single variable unknown variable n phi. So, that is done, and after integrating the first equation, one can get this expression of n phi 1 by r 2 sin square phi integration r 1 r 2 W r cos phi minus W phi sin phi bracket sin phi d phi, and limit of integration can be taken from any level, say one level is phi naught and another level another constant, say phi is equal to constant. So, when we take the definite integral of this equation, then constant term disappears. So, in between these limits phi into phi naught and phi as a other angle, we can find out the integral expression of this quantity, and therefore, n phi is completely known. Given the geometry of the surface and loading on the surface, we can obtain all the parameters, and ultimately after integration we can get n phi. Now, this integration has some physical meaning. We have seen earlier also. Now, just to recapitulate the same thing, I am telling it again. If I multiply this left hand side and right hand side by 2 pi r 2, then we will get here say 2 pi r 2 sin square phi I have taken here, and n phi, and inside the bracket these quantities are there. Okay. So, now what happens that this term can be interpreted, because when we see the shell surface say under the action of load and this meridional stress, that is n phi and n theta, that is developed in the meridional and circumferential direction, we can see that vertical component of n phi is can be obtained as n phi sin phi, okay. And total vertical component, that is this n phi is acting per unit length, and if I see the circumference of this parallel circle, then it will be 2 pi r, that is the circumference of the parallel circle, where r is the radius of the parallel of latitude or a circle. So, in that case this 2 pi r n phi sin phi will be your this total vertical component of n phi acting at this point. However, r can be expressed in terms of r 2, that is one of the principal radii, that r can be written as r by r 2 equal to sin phi. So, r equal to r 2 sin phi. So, therefore, this expression is developed putting this value of r equal to r 2 sin phi. So, therefore, we get a complete expression to interpret this integral expression physically. What is our interpretation? If I see this left hand side, it indicates that total vertical component of n phi, and if I look at the right hand side quantity, then it represents this you can see W r cos phi minus W phi sin phi is the net vertical load on the shell surface, and when it is multiplied by the surface area of this small strip, you can see here r 1 d phi, r 1 d phi is the width, r 1 d phi is the width, and if you see the circumference, then 2 pi r and r can be expressed in terms of r 2 sin phi. So, these are involved in the inside the integral expression. So, that means here we are getting that total load acting on the shell surface at this level in the right hand side, and left hand side we are getting the total vertical component of the meridional force n phi. So, this means that the total vertical component of n phi acting at a level should be balanced by the total vertical load acting at above that level. So, based on that we can obtain several important results, and we can solve very too many practical problem with ease. Okay. So, let us consider one of the such problem, that sometimes a shell having a discontinuity, means a shell is having a opening at the top, that is sometimes used or adapted for entry of light, and a structure, for example, a light structure is constructed over this, and the load is transferred by a edge beam. So, this is the edge beam on the shell, and this load you can see here I have drawn in a 3D view, that load P, that is the line load acting along the circumference. So, the extra load that is put here at the edge of the opening is P into the circumference, the length of the circumference. Okay. Now, this is the extra load put, but this has some discontinuity here, and therefore, the integration expression we want to avoid. So, just you want to use this physical interpretation of the integral expression to solve this problem. Okay. So, our intention is to find the membrane forces in this shell. Once the membrane forces are found, then we can easily obtain the membrane stress, because the forces are expressed as a quantity per unit length. So, if I divide the membrane forces, say n phi by thickness of the shell, we will get the membrane stress. Similarly, if I divide this n theta by thickness, we will get the other membrane stress, that is the circumferential stress acting on this shell. So, if I consider a strip here, for example, I consider a strip here of width, say this width of the strip will be say r d phi, r is the radius of the sphere. Since it is a sphere, a spherical dome, a part of a sphere, so therefore, this r 1 equal to r 2 equal to radius of the sphere. So, we use the physical meaning of the integral. Physical meaning of the integral says that the total vertical component of the meridional force n phi at any level is balanced by the total vertical force applied on the shell surface above that level. So, if I consider now a level here, so this level is defined from the, this is the edge of the opening. So, this is edge of the opening is at a angle phi naught. So, phi naught to phi. So, this is the level at any level, say at level phi we are interested to calculate this membrane forces. Okay. So, at this level let us see what will be the total force. One of the component of the total force is the line load, that is I call it a collar load on the shell. At the openings, a collar load is applied around the periphery. So, due to this collar load, this you can see the radius of the sphere is r. So, the radius of this small opening will be r sin phi naught. So, 2 pi r sin phi naught is the circumference into p. There is the total collar load, the strip loading acting on the shell above the level that we are considering. Okay. Now, let us calculate the surface load, that is due to a self weight or gravity load. So, if q is the gravity load including self weight and live load, then this at this level the radius of the parallel of latitude or parallel of circle is r sin phi. So, 2 pi r sin phi is the circumference of the parallel circle at this level phi, and r d phi is the width of the strip. So, 2 pi r sin phi into r d phi is the area of the strip, and this area multiplied by q will represent the load, the vertical load acting on the strip. Now, if I integrate it between the limit phi naught to phi, I will get the total load acting on the shell surface from phi naught to phi. So, f is found in this way. So, after evaluating this integral, we can find f, and then the f has to be balanced by the total vertical component of the meridional force at this level, that I have shown in the first picture. There is total vertical component of the n phi at any level phi will be n phi sin phi into circumference of the parallel circle at this level. So, based on that, I calculate that n phi sin phi will be your this total vertical component of the meridional force per unit length, and when we multiply it by circumference, that is 2 pi r sin phi. So, it represents the total vertical component of n phi at the level phi. So, this is to be balanced by f. So, I write this equilibrium equation in vertical direction. So, f we have obtained earlier in this integral form. Now, the task remain is to complete this integral. So, this integral is completed and it is added with this, and then n phi can be found out. This integral can be completed and it is substituted in this equation, and then n phi can be calculated. So, n phi is found as an expression involving this p, that is the collar load, then phi naught, that is the angle at the edge of the opening, and q r, q is the load acting on the surface, vertical load acting on the surface, r is the radius of the sphere. So, and phi is the level at which we are interested to find out n phi. So, we get this expression of meridional stress due to opening. Okay. By simple consideration of your this physical meaning of the integral without integration of this expression to find out n phi. So, now use the third equation of equilibrium, that is the equilibrium condition along the normal direction. So, that is given by n phi by r 1 plus n theta by r 2 equal to w r. W r is the component of the load in the radial direction or direction along the normal to the tangent at the meridian. Okay. So, if I see this the triangle, the which vertical side is represented by the load w g. So, therefore, radial component will be w r minus w g cos phi. Minus sign is taken because the positive direction of cos phi, it is in the negative direction of the phi. So, therefore, this radial load is taken with a negative sign. W phi is w g sin phi. this component. So, now we substitute this W r into this expression we substitute this W r, and therefore, we get a relation n phi plus n theta into W r into r, because r 1 equal to r 2 equal to r. So, if I multiply both sides by r, then the equation becomes simply n phi plus n theta equal to W r into r. Now, substitute W r as minus W g cos phi. Here minus W g is q. We have taken symbol q to represent the vertical load in the shell. So, after substituting this value W r as minus q cos phi, and we ultimately get this n theta is equal to minus q r cos phi plus p sin phi naught divided by sin square phi plus q r into cos phi naught minus cos phi divided by sin square phi. So, when the opening is not there, then phi naught is 0, then we get this the expression for the shell, which is closed shell. So, there was no opening in the shell. Okay. Second problem, let us consider a conical shell, and we consider here the gravity load, that is the vertical load acting on the surface of the shell. Conical shell is also common because the conical type of roof, that is umbrella type roof, is also common for small shed and other applications also, and conical vessel is also there for storage of liquid or other gaseous substance. So, therefore, we need to know the analysis of conical shell. Now, one important characteristics of conical shell is that it is a surface of revolution having 0 Gaussian curvature. So, that statement I have told you, the 0 Gaussian curvature. How can I say that it is having 0 Gaussian curvature? We know that Gaussian curvature is nothing but the product of the two principal curvatures. Now, here you can see how the shell of surface of revolution is formed. Shell of surface of revolution is formed by rotating a plane curve around a axis of rotation. Now, here the curve is a straight line, that is meridian is a straight line. So, it is rotated around it is a straight line inclined, and it is rotated around the axis of rotation to form the conical shell. Okay. Now, because of straight line meridian, its principal radius of curvature, there is one principal radius of curvature r 1, there is the major principal radius of curvature, is principal radius of curvature, because it is a straight line. So, principal radius of curvature is infinity. So, therefore, we have very special condition here, that is r 1 tends to infinity, whereas r 2 is finite. R 2 is this radius, the one principal radius r 2. So, we will now find the expression for r 2 and other geometrical parameters. Now, here from the geometry, if you see, the twice alpha is the apex angle, you can tell, and alpha is the semi apex angle. Okay. Now, z is a level which is defined from the apex. So, z is the distance measured from the apex at any level, say this level that I am showing here. Now, here the parallel of latitude or parallel of circle is having radius r. Okay. Now, you can see that r can be related with z by simple trigonometrical relation r is equal to z tan alpha. That means, r by z equal to tan alpha. So, r equal to z tan alpha. Now, r 2 is one of the principal radius of curvatures. So, r 2 now can be related to r. Now, we can see that r, this r divided by r 2 is nothing but sin 90 minus alpha. So, sin 90 minus alpha is cos alpha. So, therefore, R 2 becomes R divided by cos alpha, that is secant of alpha. Now, let us consider the slanting side, because the generator or directrix or meridian in case of conical shell is a straight line. So, it is a sloping line that we call slanted line. So, we now measure the distance S and find the expression of S in terms of other geometrical parameters, because S is now can be related to alpha and Z by a simple relation Z is equal to secant of alpha. Okay. So, ds, if I take a elementary surface of the shell here of width ds. So, ds can be found out as sec alpha dz, because alpha is a constant quantity. So, elemental surface area dA, if I want to calculate, dA will be 2 pi r, that is the circumference of the parallel circle, 2 pi r into ds. I can substitute ds here. So, 2 pi r sec alpha dz. So, this is the elementary area. Now, total surface area of the cone now can be calculated from 0 to this level or from any level from apex to any other level. So, here say I defined a level say by distance z1 at one plane and another plane it is z2. So, therefore, I take an integral with a limit z1 to z2 to find out the area of the strip between any two level. If one level is say the reference point, that is 0, z1 is 0, then we get the surface area measured from the apex. Okay. Now, here you can see that I have substituted dA and then I integrated. So, dA is 2 pi z tan alpha sec alpha dz, because r is substituted as z tan alpha, ds is substituted as sec alpha dz. So, once I get this expression, then after integration we find this area of the surface of the conical shell between the level z1 and z2 equal to pi into z2 square minus z1 square into tan alpha sec alpha. So, this is the area of the shell okay, between the two level z1 and z2. Now, because of infinite radius of curvature r1, we now have a very simple equation, because n phi by r1 will be 0, because if I put r1 as infinity here in the denominator, this term becomes 0. So, therefore, we get only n theta is equal to minus r 2 q sin alpha. So, W r is this this component of the force and q is the vertical load. So, after resolving this q along the radial direction, we get minus q sin alpha. So, n theta is found as minus r 2 q sin alpha, and you can substitute r 2 as r divided by cos alpha and r is again z tan alpha. So, ultimately this n theta is expressed in terms of vertical load and the distance from the apex, that the level where we want to calculate z n phi, we can put the level as z or distance as z, and the tan square alpha, alpha is the semi apex angle. So, one of the membrane stress is known. Second membrane stress that is n phi has to be now calculated, and we use the physical meaning of the expression. Okay. Now, at this level, if I consider the vertical equilibrium, we can see that here the n phi will be along this slanting side. So, therefore, component of n phi along the vertical direction will be n phi cos alpha. So, n phi cos alpha is the component of this meridional force at this level along the vertical direction, and it is multiplied by the circumference of the parallel circle. Circumference of the parallel circle is 2 pi r. So, therefore, we get the total vertical component of n phi. Okay. Then it is equated to the vertical force above that level. So, vertical force above that level q into surface area. So, surface area is now calculated from 0 to z. Earlier we have calculated from z 1 to z 2 any other level. Now, the upper limit, lower limit is taken as 0 and upper limit is z. So, after integrating this expression and simplifying, it becomes that n phi equal to minus 1 by 2 q into z secant square alpha. So, this is the expression for n phi. Negative sign indicates it is compression under the action of vertical load, and these are the quantities that we have used in finding the relation between this n phi and other shell parameters including the load. So, two expressions of the meridional force n phi and n theta are calculated. Okay. Next, let us consider the support of the conical shell, because the shell is supported at the edges by a ring beam. This is a ring beam or peripheral beam. So, how the forces will be transferred at the ring beam? Because if I see the component of n phi is along the slanting side. So, it has got two component, one along the vertical direction, one along the horizontal direction. So, vertical component is n phi sin alpha and vertical component will be n phi cos alpha, horizontal component will be n phi sin alpha. Okay. So, this horizontal component will now act here and will give a pressure on this ring beam. So, this ring beam now will be subjected to this tension due to this pressure. So, therefore, if I know the pressure on the ring beam, I can find out this tension in the ring beam and accordingly I can design the beam. So, F here is n phi sin alpha into r. Here the phi is 90 minus alpha, phi angle is 90 minus alpha. So, therefore, n phi sin alpha into r. Okay. Now, in the case of sphere, we use this phi and theta, and phi is measured from the vertical axis of rotation. Now, here mainly in the case of conical shell, the cone angle will be specified. So, therefore, the relationship is expressed in terms of alpha instead of phi. However, alpha and phi can be related very easily with the help of this triangle. Okay. So, therefore, all trigonometrical relation that was expressed in terms of alpha can also be converted in case of phi if want to specify the angle with respect to vertical axis of rotation instead of this the alpha, and this angle is measured from the vertical axis of rotation towards the shell surface. Now, here also, but here the slanting side is originated from the apex. So, therefore, the measurement is different from the two respective reference point. Hence, we generally take the apex angle alpha, semi apex angle alpha in case of shell, whereas in case of this spherical dome, we generally take the phi instead of alpha. Okay. Now, let us consider the third problem. A conical tank is filled with liquid of specific weight gamma. Calculate the maximum meridional and circumferential stresses and state where they occur. Okay. A conical tank is common in many cases. For example, we have a water tank which is combination of cylinder, sphere an cone. That means, this type of tank generally known as in-test type of tank. Here in-test type of water tank, that is the elevated water tank, you will find that roof cover is a spherical dome of small rise. Then the tank wall will be your this cylindrical shell. Then it will also have a slanting wall, that is like a conical shell, like a first term of a cone, and then it has a spherical bottom. Instead of flat bottom, it will have a spherical bottom. So, all types of surface of revolutions are involved in case of this type of elevated water tank, generally known as in-test type of water tank. So, conical shell analysis is also necessary when we apply it to this liquid retaining structure. Okay. So, here an example of conical tank filled with liquid. The density of liquid is gamma and water is filled with up to depth d. The semi cone angle is alpha and total cone angle is 2 alpha. Okay. Now, here we first use this expression n phi by r 1 plus n theta by r 2 equal to W r. W r is the load along the radial direction. Now, you can see the water pressure here is the W r, and water pressure acts equally in all direction according to Pascal law. So, therefore, W r equal to gamma into d minus y. So, if y is the distance measured from the apex at this level m n and d is the total depth of the water. So, hydrostatic water pressure at this level is gamma into this distance is d minus y, and this is acting outwards towards the surface. So, therefore, it is taken positive as per sign convention. So, W r is this. So, immediately we can get n theta as W r into r 2, but what is r 2? R 2 is this distance, this radius of curvature. Now, R 2 can be expressed as, because if I see this triangle, small triangle, this distance is y tan alpha, this distance is y tan alpha, and this angle is again can be converted in terms of alpha. So, y tan alpha divided by cos alpha will be your R 2. So, second principal curvature R 2 is obtained like that. So, substituting this R 2 as y tan alpha by cos alpha, we now get n theta is equal to gamma into d minus y into y tan alpha by cos alpha. This is the stress in the circumferential direction. We generally call it as a hoop force or hoop tension, and we want to calculate where the maximum value occurs. Okay. For calculating the maximum value for a given cone angle, we differentiate this quantity n theta with respect to dy. So, we will get the depth where the maximum this circumferential force will or circumferential stress will occur. So, differentiating this n theta with respect to y and then equating to 0, you can get here say it will be dy into y square, and these are other quantities are constant. Alpha is a constant. So, tan alpha is a constant, cos alpha is a constant, gamma is a constant. So, if I differentiate this dy minus y square with respect to y and equate to 0, then we get y is equal to d by 2. So, therefore, d by 2 is the position or a plane, that is half the depth of the cone where the maximum circumferential stress will occur. Let us calculate the maximum value of this circumferential stress. Substituting y is equal to d by 2 here in this expression, and after simplification you will get n theta max equal to gamma into d square by 4 tan alpha by cos alpha. So, one component of the this membrane stress is obtained, that is n theta, and its maximum value is also obtained. Now, let us find the other component. Okay. Other component is n phi, which will now be obtained using the this physical meaning of the integral expression. Okay. Now, at this level, the level is defined with a distance y from the apex. So, total vertical force F, say total vertical force F at this level m n. What are the total vertical force acting on this level? Is the load of the water in the cone and load of the water on the cylindrical part here. So, that means weight of the fluid in conical part m n o plus the weight of the fluid in cylindrical part, that is m n s t. So, now and gamma is the density of the fluid. So, let us calculate this component of the weight and then we can find the total vertical force. So, F is the volume of the cone is 1/3 pi r square into height. So, 1/3 pi gamma is the density of the fluid, y tan alpha is the radius at this level. So, this square into y, this is the volume of the cone and multiplied by gamma we get the weight of the liquid here. Then adding the weight of the cylindrical portion of the water, that is the radius of the circle is y tan alpha. So, pi r square into gamma density of the fluid into this height of the cylinder d minus y. So, after simplification we get the total weight as 1/3 pi gamma y square tan square alpha 3 d minus 2 y. Okay. Now, this weight at this level should be balanced by the total vertical component of n phi. So, total vertical component of n phi, if I see the vertical component of n phi is n phi cos alpha, and radius of the circle here is 2 pi y tan alpha. So, we get this total vertical component of n phi. So, equating this p to f, we get the value of n phi. So, equating p and f, we now write an equation 1/3 pi gamma y square tan square alpha 3 d minus 2 y equal to n phi cos alpha into 2 pi y tan alpha, from where we can extract n phi. So, n phi is here gamma y tan alpha into d minus 2/3 y divided by 2 cos alpha. For maximum value, again we differentiate n phi. So, n phi is differentiated with respect to y, because we know where the maximum value will occur and accordingly we want to calculate the maximum value. So, after differentiating we get you can see here, if you differentiate this quantity, that means y is here. So, you can multiply this term dy into 2/3 y square. So, that means after differentiation and equating to 0, you will get at y is equal to 3 d by 4, we get the maximum value of n phi. So, substituting y as 3 d by 4 in this expression back, we now get the maximum value of n phi. So, n phi max is 3 gamma d square into tan alpha divided by 16 cos alpha. Okay. So, you have understood how the different problems of surface of revolution under axi-symmetrical loading can be handled by using the physical meaning of the integral or directly using the integral also. Because in case of the axi-symmetrical loading, your two equations of equilibrium are only needed, and the second equation of equilibrium will be your this algebraic equation. So, n theta or n theta can be expressed in terms of n phi. So, first equation now can be written in terms of only one unknown quantity, and after integration we get the desired result. So, let us see an exercise. For example, a conical umbrella roof type roof is to be designed, and it is made of reinforced concrete and it is supported at the central column. So, now let us do this problem. Take grade of concrete as M20, steel Fe 415 and other data for concrete modular ratio is 13, permissible stress in steel 230 Newton per mm square, permissible bending stress in concrete is 5 Newton per mm square, permissible tensile stress in concrete as 2.8 Newton per mm square, and vertical load per unit area is 2500 Newton per meter square. So, we can take the vertical load as 2.5 kilonewton per meter square. Okay. So, this is this problem I want to solve it. So, we have seen that a conical umbrella roof has to be designed and it is supported on the central column. The height of the column is given in the problem as 5.2 meter. The base of the cone is 8 meter. Okay. The distance from the apex up to the free edge of the cone is 1 meter. Okay. So, the semicone angle alpha is here and alpha we can calculate now. So, given this data we can calculate tan alpha as 4 by 1. So, from where alpha is equal to 76 degree. Okay. Now, we take a level here and suppose the apex is denoted by the symbol O and here the plane is A, at the free edge it is BB. We have to calculate load on the surface and then we use the physical interpretation of this integral expression to get the expression for n phi. Of course, the one radius of one principal radius is infinity. So, n theta can be directly found out. Okay. Now, load on the surface AB, load on the surface is AB. We have seen that in my earlier slides, the pi z2 square minus z1 square, two levels are there. Now, here one level is say h is the total height of the cone minus at any level, say that level is defined as z square. Now, here z2 is h and z1 is z into tan alpha sec alpha into component of the load in the vertical direction. Now, only here the vertical load is applied. So, vertical load Wg is 2.5 kilonewton per meter square. So, after substituting h as 1, we get total W as pi is equal to 1 minus z square, and substituting all the value of this quantity, that tan alpha is tan 76 degree, sec alpha is 1 by cos 76 degree and Wg is 2.5. So, after simplification we get this W is 130 into 1 minus z square kilonewton. The unit is kilonewton. Okay. Now, this is now used. We consider a free body diagram of this portion AB. Okay. If I consider the free body diagram of portion AB, the load acting here is say whatever load is acting is now calculated, and this is the direction of your n phi, and the free edge, this edge is free. So, therefore, no stress is there, and you can see that total vertical component of the load n phi has to be balanced by the vertical load acting on this portion. Okay. Now, using this n phi cos alpha is the total vertical component of n phi multiplied by the circumference of the circle at this level. So, circumference of the circle at this level is 2 pi, and you can see this distance is z tan alpha. This distance is z tan alpha. So, this is equal to z tan alpha, and it has to be equated to the total vertical load that we have obtained. So, total vertical load we obtain 130 into 1 minus z square. So, from that quantity we can now, after substituting the value of alpha, substitute the value of alpha is 76 degree and simplify. We get n phi equal to 21.32 1 minus z square divided by z. So, this is again kilonewton per meter. The unit of n phi is kilonewton per meter. So, n phi we have obtained. Now, we go for obtaining n theta. We know that n phi by r 1 plus n theta by r 2 is equal to w r. Now, r 1 is infinity, because the straight line is revolved. So, the straight line having the radius of curvature as infinity. So, therefore, we directly get n theta is equal to, and w r, if I see the component of the load, this is a total vertical load, say w g, and this is your angle alpha. So, naturally this w r that we calculate w g sin alpha. So, we now get this component of the load as w r is this. So, n theta is r 2, w r r 2, w r is w g sin alpha, and r 2, as we have seen earlier, r 2 is now the radius of one of the other principal radius of curvature. Let us express this in terms of alpha and other dimension. So, if this angle is alpha, at this level, this is r 2, and this distance is your z tan alpha. So, naturally r 2 is z tan alpha by cos alpha. So, we can write r 2 as z tan alpha secant of alpha. Okay. So, n theta is w r into r 2, r 2 is z tan alpha sec alpha. Okay. After putting the value of w g as 2.5 kilonewton per meter square and the angle of alpha as 76 degree, we now get n theta is equal to w g. W g is now 2.5. So, we ultimately get the value of 40.216 z. So, this is the value of n theta, and it is kilonewton per meter run, and it is compressive. So, two expressions we have obtained, one expression for n phi that was given as n phi is equal to 21.32 1 minus z square by z, that is kilonewton per meter, it was tensile. So, we got these two expression. Now, we can go for designing this shell. Now, one thing you can note, at z is equal to 0, the n phi is unbounded, that is at the apex where the shell is joined with the column, central column, then there will be generation of bending moment. So, because the shell is monolithically built with the column the structure, so bending moment will be produced, and therefore, membrane theory will not be adequate at the junction of the shell with the column. So, therefore, away from this junction of the shell with the column, we have to calculate the forces. Okay. So, let us say at say z is equal to 0.125 meter, just little away from the apex, we calculate this value, z is equal to 0.125 meter. That is, if I see the shell structure, z is measured from here and it is the central column, it is the center. Here is difficulty, that is at this point we have infinite magnitude of this membrane stresses, especially n phi. So, therefore, let us calculate at a distance z is equal to 1 to 5 meter. Put this z is equal to 0.125 meter in this expression, n phi equal to that we have got earlier, z square by z, and we get this value as 168 kilonewton per meter. So, similarly, this z can be, this n theta can be calculated, but n theta you can see n theta is 0 here, and n theta is again maximum at the free edge, but free edge you know that there should not be any stress. So, therefore, again the membrane theory fails to predict the stresses at the free edge as well as at the edge where it joins with the column. So, we will omit these 2 points. Okay. Now, based on the calculation of n phi, we now calculate the area of steel required. Area of steel required n phi into sigma s t is the permissible stress. So, n phi is 168 multiplied by 1000 and sigma s t is 230. So, area of steel is 730 mm square. So, we provide ten phi torch steel at the rate of 100 millimeter center to center, that will give you AST slightly more than this 785 millimeter square per meter. Now, if I use 8 mm bar, I have seen that spacing becomes say around 60. So, that will give congestion in this structure. So, therefore, to avoid the congestion, I have increased the spacing of the reinforcement. Okay. So, AST we have found. Now, we have to find out the thickness of the shell. Thickness of the shell is checked based on the maximum tensile stress that is given, and we consider that the tensile stress should be omitted. So, F t is the tensile stress in concrete, and that should not exceed the given limit 2.8 Newton per mm square. Okay. Now, F t can be calculated as n phi divided by n phi is per meter length. So, this 1000 is the width into t, t is the thickness of the shell. Plus, if I take the equivalent area of steel, then m minus 1 into AST. So, substituting this n phi as 168 into 1000 in Newton, 1000 T m was 13. So, 12 into AST is 785. So, this is Ft and this should be limited to maximum 2.8 Newton per mm square. Now, from this equation the T can be calculated. T is now calculated as so this unknown T is now found out as 50.6 millimeter. So, for the design purpose we provide slightly more thickness. So, provide 75 mm thick shell. So, in this way we utilize the membrane theory to find the reinforcement and thickness of the shell structure. So, a section of the shell, if I draw for the conical shell, reinforcement is put here in the middle and then the distribution steel also may be of same steel. So, we have provided this 10 phi at the rate of 100 center to center. Also the distribution steel is provided as 10 phi center to center. Thickness of the shell is now prescribed as 75 mm. Thank you very much.